We just looked at the effect of windowing for continuous time. There's an identical effect in discrete time, which is more our focus in this class. So for discrete time, we get that the windowed signal is the original signal times the window function, and that's going to have Fourier transform. So discrete time Fourier transform, where we're going to convolve the original signal Fourier transform against the Fourier transform of the window. All right, so if W is a rectangular, which we've referred to as in the past as P big N, that's its length of N, then this is kind of the analogous version of the one we just looked at. Let me draw the window function then, and it's just now it's just a bunch of delta functions out to L minus L, so the entire length N is 2L plus 1. Okay. We studied this a month or so ago, and we found that if we take the Fourier transform, discrete time Fourier transform, we get that the result is a Dirichlet function, which is given by this thing, sine of omega n over 2 over n sine omega over 2. So this is periodic. Everything, since we're in sampled domain, everything's periodic, and this is a periodic. Some people call it a periodic sinc function. And so it looks like a sinc function, except it repeats. Okay, I'm just going to draw the part in the fundamental range. It has an amplitude of 1, and it has a zero crossing right there at 2. So we have this fundamental relationship that if the width is n in the time domain, the first zero crossing of the sinc function is 2 pi over n. And here it's a periodic sinc function. Okay then, thing to notice is that big N, big observation window, observe lots of samples, makes this sinc function really narrow because n is in the denominator. Alright, let's look at the example we just looked at, but now for discrete time. We have x of n as a cosine, omega naught n, so its frequency is omega naught radians, and it has again a discrete time Fourier transform if we allow delta functions that looks like this. And this is just one period. This has to be periodic. So what I'm showing here on in the math is only one period. I could write this out and show that it repeats every 2 pi. So this is only one period between minus pi and pi shown. Okay, that's what this is. Just to simplify, we don't need to get real rigorous about this. So this repeats every 2 pi. And that means that, so this is the time domain thing, and the frequency domain picture looks like this. So it's got delta functions at omega naught and minus omega naught. And if we really wanted to show the rest of these periods, and maybe I'll do that right now just to remind everybody, at 2 pi we get another image of this. So we pick up, we start repeating this image. There's 2 pi minus omega naught and 2 pi plus omega naught, etc. Okay, so this goes on forever in both directions. Alright, so this is x e to the j omega, and we're going to convolve that against this Dirichlet function. Okay, and once again, whenever we convolve something with a delta function, we're just going to make a copy of this at every place there's a delta function. And so, same logic applies. I'll just kind of sketch out what we get. Here's the frequency axis. So we'll get a sync-like thing there, and a sync-like thing there. And again, this repeats forever. So this is the windowed Fourier transform. And I'd like to say, of course, this is 2 pi, that whenever we take the discrete Fourier transform, remember we're interested now in trying to estimate this thing using a DFT. We're going to get, let's see if this will work. We're going to get results that are between 0 and 2 pi. So I'm just going to spray paint this. What the DFT shows us, this is an awful graphic, but you get the idea, I hope. What the DFT is going to give us is everything between these lines, oops, if I can get my pen back, everything between there, between 0 and 2 pi, this is the fundamental range. Okay, so bad graphic, sorry about that, but this is what we're going to see. And I'll point this out multiple times, but when you get this frequency display, and I'll ask this on the test, I'll say, okay, tell me how many sinusoids are present. Your job is to say there's one sinusoid present, because there's one line. You'll also see this thing, but don't be fooled. This is just the folded, this is folded about folding frequency, pi, and so this is just an image, okay, it's an alias. So this isn't actually a sinusoid that we're interested in. Everything between 0 and pi is what's going to make it out if we send this to a digital to analog converter. So before I end this little segment, let me do a quick kind of example of the kind of calculation that you need to be able to make. Let's suppose we get something that looks like this. Let me draw this with kind of a dotted line. And of course we'll draw its alias in here as well. The reason I'm drawing this with a dotted line is that when we do a DFT and we get x of k, we're actually going to sample this thing at regular intervals. Okay, so we're going to do something like this. The DFT is not going to be able to, with a computer we can't calculate all infinite number of frequencies, so we sample the discrete time Fourier transform at these points. So suppose we have a peak at k equals 5. Okay, so this is the discrete Fourier transform. We get a peak here, and we want to know what frequency that corresponds to. What frequency corresponds to k equals 5? Well, I can't tell you right away because I have to know the sample rate. So let's suppose the sample rate is given as 1,000 hertz, 1,000 samples per second. We still don't know enough data. We have to know how many data points we were measured to get the DFT. So let's say that n is equal to 20. And now we're in good shape. In terms of the DFT, 2 pi, this place up here, corresponds to n. Okay, so we would take n samples in time. So this is Bn. So there are n samples spread across 0 to 2 pi. So that means that every distance between two samples in the frequency domain is 2 pi over n. Remember, the whole range is 2 pi and there's n samples. And now we know that k equals 5. So we've got 5 delta omegas here. So the frequency of the sinusoid is k 2 pi over n, which is 5 2 pi over 20. Oops, excuse me. That's I said that wrong. This is not the frequency in hertz. This is the radian frequency. Okay, so there's 2 pi radians, and so that's equal to pi over 2 radians. All right, so what frequency in hertz does that belong to? Well, F naught is equal to 2 pi excuse me. So okay, wait a second. I got started on the wrong foot here. Let me back up. F naught, the frequency of interest, is going to be k times delta f. Okay, k is 5, and what is the frequency in hertz between these samples? Well, the highest frequency here also corresponds to the sample rate. So big N corresponds to the sample rate f sub s. So delta f has to be fs over n. Right? So there's k times delta f. 5 times, what do we have? 1,000 over n, which is 20. Which is 250 hertz.